we need a more rigorous way of labeling enantiomers, labeling stereocenters, really. And to get there, we're going to use a formalism called the Kahn-Ingold-Prelog formalism. This is one of the most important topics that we'll cover in the class. It's R&S nomenclature is what it's called for all the former students. They'll be like, oh yeah, that was an important part of the class was R&S. Okay, anyway, let's get right into it. So what we want to do is use the Kahn-Ingold-Prelog. It's 3 scientists. I don't know any of them. I mean, I don't know what they did beyond this. So we want to use the Kahn-Ingold-Prelog method for labeling stereocenters. And this is also called the R/S nomenclature. Okay, so what we want to do is be able to label the stereochemistry of a molecule from the molecule's structure. Now, this is not at all related to optical rotation. Optical rotation has to do with identifying that a molecule is chiral based on its interaction with plane polarized light, chiral light, if you will. But this has to do with taking the bond line structure and labeling its stereocenters with some sort of label so that we can tell the difference as opposed to saying it's a wedge or a dash. Okay, so what we're doing is we are analyzing each stereocenter and labeling the stereocenter as R/S, or really as either R or S. R or S. So we can have one of these 2 labels. What's really nice about this is it allows us to look at a bond line structure and label R and S. And if we do this accurately or correctly, then no matter how the molecule twists, turns, rotates, as long as we don't break the wedge and convert it into a dash. But if we roll the molecule over so that the back is now the front, everything that we assign to be R in one orientation should be R in another orientation without sort of actually, if we wanted to go from R to S, we should have to break bonds. So what does this mean? What does R and S mean? Well, R, it's kind of has a weird history, but R has to do with rectus is what it's short for. And I sort of think of it as right, like a right-handed sort of thing. Again, the names we'll see in a second, this isn't great, but rectus is sort of short for righteous. I'm uncomfortable because S is supposed to be our left version, but it's the opposite, sinister or left. So that always makes me uncomfortable that we labeled the left-handed form of something or the left version of something as sinister. It's just Latin words. It really is just Latin. So let's just stick with that. Let's assume that these chemists, maybe it's not a good assumption, but let's assume that these chemists weren't actually thinking that left-handed people were still possessed by evil spirits, which was a thought, and it's not part of the history of humanity that we really like to look back on with glowing eyes. Anyway, so we have R and S. R is like right-handed, S is like left-handed. They stand for rectus and sinister, but the only people that ever say those words anymore are the people that really are infatuated by the history here. Okay, so we've got R and S. Now what we want to do is take a chiral molecule and identify the stereocenters not only with a star, but also with an R or S label. Okay, so let's do that. Let's take this molecule, and we're going to label the stereocenter, which is, again, our carbon with 4 different things attached to it, as R or S. Now it's the stereocenter. That means we have one carbon atom being labeled, and it's not the entire molecule. Okay, so an R and S correlates to one particular atom within the molecule. Okay, so it's not like the overall molecule. And that's important as we look at molecules with multiple stereocenters. Like if we have 2, one could be R, one could be S, we could have RR, SS, that sort of thing, various combinations. How do we do that? So number 1 is we need to locate the stereocenter. And the wedge / dash must be included. If not, we cannot determine the R&S label because the stereochemistry has not been defined. It's still a stereocenter, could lead to a molecule that's overall chiral, but if we don't have the wedge and the dash, we can't do this little trick of labeling an R or an S. Okay, so we have to first locate the, and if we, it's not hard in this case. We've got our wedge and our dash, and we just put a star next to where the wedge is. Okay. Now, the important one is this step. That is, we need to prioritize the 4 groups attached as 1, 2, 3, and 4. Now, what I mean by prioritize is we need to rank the atoms directly attached. And so highest priority is 1. Highest priority is 1. Then it goes 2, 3, 4, and 4 is our lowest priority. Okay, so that's how we are going to rank the atoms. What did I draw? I drew, okay. Let's get the molecule in front of us again. So we're looking at the atoms that are directly attached to the carbon with a star. And so the highest priority element is going to be the heaviest. So prioritization, priorities, let's do this. Priorities are hydrogen is always the lowest priority. If you've got hydrogen on a stereocenter, it gets to priority 4 right away. So it goes hydrogen, carbon, nitrogen, oxygen, fluorine, chlorine, bromine. It's really by increasing atomic weight. Okay, so and these, we'll sort of just stick with hydrogen, carbon, nitrogen, oxygen, fluorine, then the rest of the halogens after that. So if you look, it's increasing atomic weight. Hydrogen's the lightest element, so it's always the lowest priority. In fact, we can even look at that right up here where we have the hydrogen. Now, hydrogen is not written explicitly, so we have to include it. I like to just draw it outright. And in this case, it's going to get the dash. It's always kind of that missing group. It's usually a dash, but sometimes it's a wedge. And if it's a wedge, we have to pay attention to that. So I'm going to draw the hydrogen into my stereocenter with a dash in this case. And I'm going to just emphasize that that's going to be our lowest priority, which is priority 4, the highest number, strangely. Well, just by definition, somebody decided that. Okay, highest priority goes to the highest atomic mass element directly attached to the carbon that's a stereocenter. That's going to be, in this case, bromine. So bromine gets to be the highest priority. Now, number 2 and number 3 come from a tie of carbon elements. That is to say, we've got a carbon at this position and a carbon at this position. Maybe I'll highlight those in a separate color so you can see them. So 2 of our groups that are attached, they're different. One's a CH3 and one's an ethyl group, so methyl group and an ethyl group. And what we'll see is in this particular case, the ethyl group is a higher priority than the methyl group. So methyl group gets 3, ethyl group gets 2. The highest atomic mass element directly attached is bromine. For now, if you like being like, oh, that makes sense, ethyl, if we have to rank groups, ethyl group should be, and we're going by mass roughly, maybe ethyl group makes sense to be the number 2. And that's fine for now. We're going to get into a more stricter definition in a second. Okay, but I want to at least get to our R and S. So we have, our priorities are 1 for bromine, 2 for ethyl, 3 for methyl, and 4 for hydrogen. Okay, now in step 3, let's see, where are we at? I have this like step system. Okay, so in step 3, and this isn't going to make a lot of, this isn't going to be too meaningful at this point, but in step 3, we want to rotate the molecule. So number 4 priority is a dash. So number 4 priority is a dash. Well, do we have to do that in this case? Just redrawing the molecule again. I'm going to include the implicit hydrogen shown as a dash. So we have 1, 2, 3, 4. So 4 is already a dash. So it's already a dash. Okay, cool. If it's already a dash, then there's no need to rotate the molecule. Okay, so there's no need to rotate the molecule in this case. And we can move on to step 4. So step 4 is the last step. So now what we're going to do is draw a circular arrow connecting, and you have to go in this order, 1 to 2 to 3. Now what about 4? Not 4. 4 is in the back. So we ignore 4. So we're going to draw a circular arrow from 1 to 2 to 3, ignoring 4 altogether. 1, 2, 3. So my circular arrow is going to look like this. Now with our circular arrow drawn, we're going to inspect that arrow. If the arrow is clockwise, then we have an R stereocenter. If the arrow is counterclockwise, we have an S stereocenter. So with this particular arrangement, having prioritized the groups 1 to 2 to 3, and I always like to focus on the elements that are directly attached. Number 4 is in back. We connect 1 to 2 to 3. That arrow is moving counterclockwise. If it's a counterclockwise arrow, then we label this as S. So the stereocenter here is S, and that's sort of, I guess, the answer. Okay, so those are kind of the steps. We prioritize the groups. We rearrange the molecules so that number 4 is in the back or a dash. And then we draw an arrow connecting 1 to 2 to 3, never to 4. We ignore 4. Okay, connecting 1 to 2 to 3. And then if it's clockwise, we're R. If it's counterclockwise, we're S. That's what we do. Every stereocenter. So if we have multiple stereocenters, we do this multiple times. Now, there's some things we need to consider, namely enantiomers. They flip all wedges and dashes. And as a result, they flip all R's to S and vice versa. Okay, so what I'm saying is that our rules where we flip wedges and dashes around as we go from enantiomers between enantiomeric structures and diastereomeric structures, those rules also apply for R and S. And once you get one, you kind of get them all. So for example, if we did the exact same thing on this molecule, okay, we have the exact same groups, so we can go ahead and prioritize this quickly. Bromine is 1. I'm going to draw that label as close to the atom that's directly attached to my stereocenter. 2 for the ethyl group, 3 for the methyl group, 4 for the hydrogen. Okay, so at this point, if we connect 1 to 2 to 3, we have a clockwise arrow. Oops. Don't forget that one rule where we have to rotate the molecule around so that we put the number 4 substituent in the back. So rotate. And I'm just going to pick up one side and spin it around. Let's see if I can do that with the camera. Okay, I'm going to spin it around. And if I do that 180 degrees, 1/2 turn, then my methyl group is on this side, my ethyl group is on this side. Here's my star, and my wedges go to dashes. Okay, so 1 to 3 to 2 to 4. The priorities also just kind of flip around. Now, when I do that, I can redraw my arrow, and I don't have to put an oops next to it. 1 to 2 to 3. Now we're moving clockwise. So instead of this arrow, now we're moving clockwise, and if it's clockwise, then it's R. Okay, so between enantiomers, we can make the claim that enantiomers have opposite RS assignments. Enantiomers have opposite RS assignments, so if we compare this molecule to this molecule, we would call this molecule an S molecule and this molecule an R molecule. I make sure that label is readable, but I also make sure it's close to the carbon. Maybe I even do one of these where I recognize that I want to show my work so that Willoughby knows I was thinking through everything. So I've got my priorities listed. I even wrote the number 4 substituent and back. I connected my arrow. Gosh, this is getting sloppy. But I showed all of my work, and now I'm just going to have an arrow pointing to the carbon, just to communicate to Willoughby that I know that an RNS label goes on a stereocenter within a molecule. It's not for the overall molecule. Okay. So I guess before we break, let's look at diastereomers really quick. It's not too hard if we've gone this far. Let's pick a different group to attach. So we have, that'll work. That'll work. Okay. So we've got this molecule, and I want to assign R/S to all stereocenters. In which case, in molecules like this, I like to draw them nice and big. Willoughby was nice because he didn't put hydrogen in front. We'll look at that in a separate lecture. So hydrogen, for every wedge, there must be a dash. I draw the hydrogen atom. I label it as 4 because there's nothing lower priority than a hydrogen. Now, our stereocenters are at these positions. If I focus on this stereocenter first, I'm going to label my oxygen as 1. That's a high atomic mass element. I'm going to call this stereocenter A and B. So star A has got for 1, 2, 3, 4. Priority 4 goes to hydrogen. Priority 3 goes to carbon. Priority 2 goes to carbon. And that's because priority 1 goes to my OH. So I've got 1 and I've got 4 figured out. And that's actually true for both of them. There's a lot of symmetry in this molecule, but it is chiral. You can't draw a meso. This is not a mesoform of this molecule. Okay. So we've got stereocenter A. Now, how do we assign 2 and 3? If you look, we've got 2 carbon atoms. Now, in terms of overall mass, the carbon elements tie each other. But just like we saw before, we're going to give the methyl group a lower priority than the other big group. Like, look at how big this is compared to just that little CH3. Okay, so we're going to go to, I'm going to label this rest of molecule. And then this is going to be CH3, so 3. Now for star A and B, we actually have the same priorities. So this gets a little confusing. We've got a 2 down here that corresponds to that stereocenter being number 2 priority for stereocenter B, then 3, then 1, then 4. All right, so focusing only on one stereocenter at a time. Let's start at star A. We're going to go from 1 to 2 to 3. That looks like this is an R stereocenter because we're moving clockwise. Now stereocenter 2, we'll use, I don't know, we'll use blue. So for stereocenter 2, we have blue. We'll connect from 1 to 2 to 3. You can see this really starts to get complicated in terms of showing all of your work, so it's important to properly label. Now 1 to 2 to 3, that again looks like it's going clockwise, so it's again R. So the molecule ultimately was RR. We could show our work by having all of the priorities labeled, and we show the arrows connecting our molecule. We didn't have to do any fancy rotations and that sort of thing to make sure that our number 4s were in the back. Okay, so that's a pretty heavy introduction to Kahn-Ingold-Prelog, which is again just 3 scientists that developed this approach to making note of how stereocenters were actually different from one another. We're going to use this in a few lectures upcoming, look at all the little nuances, the tricks, that sort of thing. In particular, pretty soon we have to figure out how to more strictly prioritize carbon groups, because as you can tell, in almost every stereocenter we see, we're going to have multiple carbon atoms. So those things are going to have like an atomic mass tie that we have to know how to deal with.